Let's move on to section 6.7, which is on cardinality of number systems. So we're looking at this whole discussion of cardinalities of sets. So we said that there were these different ways to describe cardinalities. We had something like finite. We had something that was countable. So finite, you have the same cardinality as some set 1 through n. Then we had countable. Countable, we had countably infinite. Countably infinite was the one that has the same cardinality as the set of the natural numbers. We had countable, which was either going to be countably infinite or finite. We also had infinite, that said that you're not finite, and we had uncountable, which said that you're not countably infinite, or you're not countable. So we had these 5 different ones, and we were able to separate them into different categories. And then we saw some other results, like we saw, for instance, that we have an infinite number of sizes of infinity. Then we saw that the natural numbers has a different cardinality than the power set of the natural numbers, and that has a different cardinality than the power set of the power set of the natural numbers, and so on and so forth. So we have this giant string of all of those. But let's go back into the types of numbers that you're used to looking at again before we start trying to ask questions about power sets of things. Because I don't even know how you'd make the power set of the natural numbers, to be honest. It's kind of hard, so I don't really know. But let's look at things. So first off, to try to show something is countably infinite, remember we said that has the same cardinality as the natural numbers. To do this, we can simply write down all of the elements in a list. So if I can create a list of numbers that includes every single one of them, then that is going to be countably infinite. So for instance, if I was to look at all of the integers, for instance, I could make a list. I could do 0, 1, -1, 2, -2, 3, -3, and so on and so forth. This list technique is one of the easiest ways to try to show something is countably infinite. This bijection between these two sets is formed by a list. So why is there a bijection between a list and the natural numbers? Well, if we think about this entry, this is our first entry. This is my second. This is my third, and so on and so forth. So there's really a bijection between this and the number 1. Bijection between this number 2 here, 3, call this one 4, call this one 5, and so forth. So this is the set of all the natural numbers, and you're now creating a bijection, this one-to-one perfect mapping with the natural numbers as well as the set of all the integers. So that's why it's okay to do this. So with that approach, we can now start to ask other types of questions about what things can we form a list with and what things can we not form a list with. So the set of all rational numbers, is it possible to make a list of every single rational number? So if you think about how you could start doing this, let's say, for instance, you're like, okay, well, I have 1 as a rational number. All right. Well, I also have something like 1/2, and I also have something like 1/3 and 1/4 and 1/5, and so on and so forth. But this is not going to give me all the rational numbers, right? If I do this ... this just gives me all of them of the form 1/n. I don't even get to 2, right? This just gives me not all of them. But you're not allowed to just say, okay, continue on with that pattern, and then when you're done, then we'll start at 2, because you're never done. You're just going to keep going. So you never get to this point of 2. So you're not allowed to make the list like that. So it seems like maybe we won't be able to make a list of all the rational numbers. However, there's this little fancy technique that some brilliant mathematician came up with, where what if I start to write out rational numbers in kind of a double coordinate system way. So if I'm going to do this, I'm going to do 1, 1/2, 1/3, 1/4, 1/5, and so on and so forth. But then down on this way, I'm going to change the numerator. 2/1, 3/1, 4/1, 5/1, and so on and so forth. So in this way, I change the denominator. In this way, I change my numerator. And I'm going to form this giant grid. So then this would be 2/2, this would be 2/3, this would be 2/4, 2/5, and so on. 3/2, 3/3, 3/4, 3/5, 4/2, 4/3, 4/4, 4/5, and so on. Okay, so this is going to list off every single one of them, but it's not a list, right? A list is I have a first, a second, a third, a fourth. This is not a list, but we can make it a list. So the strategy that they came up with is I'm going to start with this number, and then my next number is going to be 1/2. Then I'm going to go this way, and then I'm going to go down, and then I'm going to go diagonal, and then I'm going to go over, and then I'm going to go diagonal, and then I'm going to go down, and then I'm going to go diagonal, and I'm going to go over. And so notice with this pattern, this listing way, this pattern that I formed, I'm going to be able to hit every single rational number. Every single rational number will be put into this, I guess, as a note. I'll get back to that. But so if all the rational numbers can be put like this, then indeed I'm able to form a nice, clear way where I'm able to hit every single one of them. Two things that you might note. One, you're like, wait a minute, these are duplicates, right? 1/1 is the same thing as 2/2. Well, if you get rid of those, you just remove them from the list. We don't actually need to have like the list specifically given. It just has a way to make sure that we have every single one of them is going to have a buddy. But the other thing you might be noticing is, wait a minute, this isn't all of them. This is only the positive ones. What do we do about the negative ones? Or even something like 0. Well, we can make do with that, right? This was the hard part. But if we want to include 0, just put 0 over here. Start with 0, hooray. Then if you want to include negative numbers, every time you include one of these, include its negative right afterwards. So you'd have 1/1, the next one would be -1/1. Then you'd have 1/2, the next one would be -1/2. Then you could do 2/1, the next would be -2/1. So you can make this strategy work. And so what we see here is that the cardinality of the rational numbers is the same as the cardinality of the natural numbers. So these two, the set of rational numbers is countably infinite. It is not uncountable. It is countably infinite, has the same cardinality as the natural numbers. So then the next largest kind of common set is what happens if we look at the set of algebraic numbers. So these are the roots of polynomials with rational coefficients. So all of the rational numbers are going to appear in this list, right? So for instance, if I take the number b over a, so if I'm trying to figure out what polynomial is this a root of, well, this would be b minus x times a is equal to 0. Plug this in there, I'm going to get all of this equals 0. So this is a polynomial. Great, it's the root of it. Awesome. So every rational number is a root here. The other ones, though, these are also roots of polynomials. So for instance, x squared minus 2. If I look at where does this equal 0, well, I'm going to get now plus or minus the square root of 2. So I can now include square roots. I could include 2 times the square root of 2. I could even include something like the square root of 2 minus the square root of 3. I can come up with rational polynomials that have rational coefficients that make this work. So you now then get to add in a whole bunch of square roots. You can also add in cubed roots, right? Because you have something like the cubed root of x minus 2 is equal to 0. The root of this would be the cubed root of 2. So algebraic numbers now give us a whole lot more to work with. So does this have the same cardinality as the set of natural numbers? Well, yes. So indeed, this has the same, I don't remember what notation they use for this, but the cardinality here, this is the same as the cardinality of the natural numbers. So this set is also countably infinite. So it is not uncountable. We have the same cardinality of natural numbers. So just another result that if we add on a whole bunch more, we still get the same cardinality.